Okay, we're moving on to 14b. So we're going to look now at e. So e is just a special case. Before we did like 2 to the power of x and 3 to the power of x and so on. So we'll get to e in a moment, but what I want to do is I'm just going to show you these are the functions, and if I have these functions, this is the gradient function for each. Don't worry about calculating the gradient function yet. You're not expected to be able to do that yet. Okay, I'm going to do that for you, but I want you just to notice the pattern. So if we have the graph on the left, what is the gradient function on the right? In other words, what do you get when you differentiate? Well, there we will just get 0. That kind of makes sense because 1 to the power of x just means it's always 1. So you have a flat line, so the gradient is 0. If you have 1.5, this is what you get when you differentiate. You get 0.41 multiplied by 1.5 to the power of x again. Again, you don't need to know where that comes from. Just look for the pattern. 2 to the x. So it's got itself there and this number in front. Itself, this number in front. Itself, this number in front. 2.5, itself, and this number in front. 3, it has itself and 1.1. And again, 3.5 has itself and the number 1.25. So you might ask yourself, well, what's going on? There must be some number in between 2.5 and 3 where you would get 1 multiplied by itself. In other words, there must be some exponential where you differentiate it and then you get the same thing back. So it's the same as its derivative, which is rather unusual. So what's going on? Well, in between 2.5 and 3, there's a special number called e. This is one of these irrational numbers, okay? So you won't be able to type it in neatly. And it has this unique property that when you differentiate it, it stays as itself, okay? So you're expected to use this because differentiation shows how things change. So if we have a model with exponentials and we want to see how they're going to change, we need to differentiate. So that's why this is important. So as you see over here, if we have y equals e to the x, when we differentiate, we get e to the x. Now, we're going to use this, but also there tends to be something in front of the x quite a lot. So we're going to call this coefficient k, the coefficient of the x. If we want to differentiate this, our rule is we sort of just bring the k part down and the e with the power part stays exactly the same. So let me show you what I mean. E to the 5x, well, you take the 5 down to the front, but the e to the 5x just remains the same. Okay? E to the minus x, so that's effectively there's a minus 1 in front of the e. So you bring the minus 1 down, and then the rest of it you keep the same. Okay? Just like that. If there's already a number there, that's fine. Keep the number there, bring the 3 down with it, and then in differentiation, those constants at the front, we multiply them together. So we get 12, and then the e to the 3x part, again, is exactly the same. So pause the video, and I'd like you to have a look at these ones here and think about true or false. What they do is they say, if you differentiate this thing with respect to x, you will get this. So in other words, they're saying, does this become this? Does this become this? Does this become this? And so on and so on. Pause the video, have a quick think. The rule is that e to the kx becomes ke to the kx. Or even more generally, if there's a number there before, you just put that with the k as well. So I'm assuming you've done that. Have a look at the answers there on the board. So what's wrong with some of these? Well, you only put the number in front of the x. You don't put the x itself. That's why that one's wrong. What's wrong with this one? Well, the 2 has moved down. That's correct. But the remaining part must be the same as before. So it needs a 2 there. Okay. Right. So now we know what e is. We can kind of put a and b together. So e to the x is just an exponential. Okay. That again would go through 1. So what about e to the 3x? Well, this is a transformation inside the inside the function. So it's going to affect the x direction in the opposite way. This will be a stretch by a scale factor 1/3. So black is the original line. It would become something here like the blue line. So it's important that the points move closer. So they're moving in this way, and the 1 is still there. You still have an asymptote at y = 0. What about 5e to the minus x? Well, we said that if you have a fraction, or if you have a number greater than 1 with a negative x, this will be a decay. So this will be a decay as well. So the black line is the original. It decays, and it went through 1. The 5 is outside the function, so it will stretch in the y direction by a factor of 5. So notice also that the y-intercept changes there. If you have something like this, consider doing this part first and then this part next. So you could read this as e to the third x plus 2. So I would do the e to the third x element, which is going to be stretch it by a factor of 3 in the x direction. And then I will shift the whole thing up by 2. So let's show you a neat example of that one there. So something like this. The black line became sort of, more spread out further away from the y-axis, but then everything has shifted up, and this has been drawn in one step. If we shift it up, then it's actually going to shift up the asymptote. So y = 0 will become now y = 2. So it would be really important to make sure that you mark that. Pause the video and have a go at this one here. So try and break it up into steps. You may even wish to start by drawing an e to the minus x graph. That might be a good starting point, and then work through the steps. So once you've done that, you should have something like this, okay? It goes through the origin, this one. So it used to go through 1, but because everything's been shifted down by 1, it will go through 0, and the asymptote is drawn on there clearly. If you only have this e to the minus 2x, yes, you can't really appreciate the visual difference of e to the minus 2x and e to the minus x if they're not both drawn on the graph. So don't worry about the fact that you can't so much see this, this compressed stretch by a half in the x direction. Okay, that's quite natural for a graph like this. So this takes you to 14b.